Hello, this is Aya Hussein. Today I'm going to present our work on swarm collective wisdom, a fuzzy-based approach for confidence estimation. Group decision-making literature focuses on studying techniques for fusing individual opinions in a way that makes a collective decision that is as good as or better than the best individual's opinion. Many social insects and animals exhibit collective decision-making. For example, to select a nest of high quality or the shortest path between its food source and home. The interest in group decision-making has also extended to robot swarms. And by robot swarm, I mean a large group of robots, each with limited capability. These robots deploy local interaction and communication to achieve complex tasks that are beyond the capabilities of single sophisticated robots. Collective decision-making has different applications in robot swarms. For example, by exploiting their spatial distribution, these swarm members can accurately classify gesture commands given by their human supervisor. And here, collective decision-making is used to enable swarm members to select the shortest path between 2 points. Recently, the distributed feature detection problem was proposed by Valentini et al. As an abstract problem that allows for developing domain-agnostic swarm collective decision-making algorithm. The problem considers a grid-based environment in which the color of each cell can be black or white. And the task is to use the swarm to find out whether the environment as a whole is mostly black or mostly white. There are 3 objectives to be achieved by the algorithm. First is to achieve high decision accuracy. Second, to achieve high consensus or majority rate. And third, to achieve high time efficiency. There are also some constraints on the actions each swarm member can do. First, an agent can only sense the color of a cell it is in. Agents can only communicate with other agents within their communication range. At any time step, an agent can either sense the color of the environment or broadcast its opinion, but not both together at the same time. And finally, no built-in positioning capabilities are assumed. These researchers proposed 3 state-of-the-art algorithms to solve this problem. The algorithms are similar in terms of opinion sharing as follows. All the algorithms use binary representations for agent opinions. Also, all the algorithms allow more confident agents to have more influence in the decision-making process. This is by allowing confident agents to broadcast their opinions more often. And these algorithms, each agent estimates its confidence according to this equation, maximum of the number of white cells and black cells it encountered over the total number of cells the agent observed. This means that agent confidence reaches its highest level when all the cells it encountered have the same color, so all black or all white. Also, the confidence reaches its lowest level when the agent encounters the same number of black and white or equal number of black and white cells. The algorithms are different in opinion fusion. So the received opinions are fused in the Volter model such that the agent randomly copies any opinion it receives. In the direct comparison algorithm, an agent copies an opinion it receives only if the confidence of the received opinion is greater than the agent's own confidence. And in the majority model, An agent applies a majority rule on all the opinions it receives, including its own opinion, to set its new opinion. This is also in environments where one color is much more frequent than the other. In these environments, agents are likely to have correct opinions, their confidence will be high, which means they will communicate more often and quickly reach consensus. And this setting actually represents decision-making scenarios with consistent pieces of evidence. However, in environments with close numbers of black and white cells, each agent becomes less likely to have a correct opinion. And also the average confidence approaches its lowest level of 0.5. So when the confidence decreases, the average confidence, the average confidence reaches its lowest level. And when the confidence decreases, also the communication decreases, which means that the decision-making process will take much more time. And actually, this scenario represents decision-making scenarios where the pieces of evidence are inconsistent. So each piece of evidence can lead to conflicting conclusion. Also, in non-homogeneous environments, where the feature distribution can vary widely between different environment regions, the state-of-the-art algorithms will fail because confidence will be very high for all the agents, for most of the agents, regardless of whether they have correct opinion or not. And these scenarios represent decision-making scenarios with sample bias errors. Now I'll present the proposed algorithm that builds on the state-of-the-art algorithms while avoiding their weaknesses. The main contribution of our algorithm is its ability to estimate confidence reliably. So we as human beings tend to estimate confidence based on the consistency of the pieces of evidence we encounter. And this does not necessarily correspond to the accuracy of our decisions. So the state-of-the-art algorithm uses the same technique to evaluate agent confidence. But a reliable estimation for confidence can be achieved if the calculated confidence is proportional to the actual probability of being correct. Here, we define a state variables that are relevant to the reliable confidence estimation by an agent. The first variable is the number of observations an agent makes. We know from statistics that as the sample size increases, the accuracy of the agent also increases as well. The second variable is the consistency of observations. So if the pieces of evidence an agent encounters are inconsistent, this is an indication that the problem is difficult, at least from the point of view of that agent. And these two state variables are relevant for single agent decision making. But as we move to the multiple agent case, more variables can also be utilized to calculate confidence even more reliably. So state variable 3 is a perceived degree of agreement, or what we call quorum, between other agents. And the last state variable is about whether or not the agent's own opinion agrees with the perceived collective opinions of the other agent. So if other agents highly agree on a certain opinion, which is also the same as the agent's own opinion, this can be an indication that confidence might be set high. So after using these state variables to define its state, an agent needs to map this state to a confidence level. And it's worth mentioning that the relation between these state variables and confidence is not necessarily a linear relationship. So a simple linear model will not be sufficient. We propose the use of fuzzy inference system to learn the mapping between approximate the mapping between agent state to its confidence level. The main advantage here for the inference system is its simplicity and low computational complexity, which allow for their deployment on the simple robot swarm members. We use 5 fuzzy sets for the first 3 variables, but only 2 sets for the last variable, which is a binary variable. We used hybrid neural fuzzy inference for learning the mapping between agent state and its confidence level. And so we ran training scenarios with different feature ratios and feature distribution. And in all these training scenarios, we kept agent confidence fixed at 0.5. Data were then logged from these scenarios such that at each time step, all the state variables for each agent or the state variables are logged together with a binary variable indicating whether the current opinion is correct or not. This resulted in 38K rows of data. Then rows with similar values for state variables are aggregated together. So the first 2 aggregated together, and the second 3 rows aggregated together. They aggregated together, and rather than using a binary variable for opinion correctness, we calculate the average of opinion correctness among similar states. The aggregated data is then used for training the fuzzy inference system. To evaluate the performance of the proposed algorithm, we ran some simulation experiments in which the environment size was 150 times 150 grids. We used a swarm of 100 agents, and we used time limit of 500 simulation minutes. We used the very same simulation platform with the same agent capability for all the competing algorithms. Now, the results, the performance of the algorithms is evaluated in terms of a number of performance metrics. First, accuracy is calculated as a percentage of agents that have a correct decision at the end of the scenario. So for homogeneous environments, 100 accuracy was achieved by all the algorithms. But in non-homogeneous scenarios, the accuracy of the algorithms, all the algorithms decreased as the feature ratio approaches 0.5. The proposed algorithm maintained a very high accuracy in all the scenarios, with its lowest accuracy being above 95%. Second, the majority rate is the percentage of runs where the swarm member achieved at least 90% agreement on the final decision. In homogeneous environments, also 100 majority rate is achieved in all these scenarios by all the algorithms. In non-homogeneous settings, the majority rate also decreased as the feature ratio approaches 0.5. Only the proposed algorithm kept its 100% majority rate in all the scenarios. And similar results were also obtained for the task time in both homogeneous and non-homogeneous environments. So in summary, the proposed algorithm achieved the best overall performance as measured by the 3 performance metrics just presented. The performance gains achieved by the proposed algorithm did not require any additional resources. Rather, it relied on the reliable confidence estimation. We as human beings have considerable and well-documented issues with confidence estimation. Ironically, these issues were transferred to algorithms for swarm decision making. If the proposed technique demonstrates that it works very well with swarm members, this poses the question if of whether a similar solution can be proposed for decision making in human groups. Thank you.